All right, welcome back, everybody. Welcome to our online notes here. Today we're going to keep talking about Taylor series that we introduced right before break. Just remind ourselves real quick of what that looked like with our first day thinking about these. We took the alternate approach. Instead of a kind of bottom-up point of view, which was more from 11.9, looking to relate everything to 1 over 1 minus something, and to see what we could get from that. Now we're taking more of a top-down approach, where we start by just assuming that our function can be written as a power series centered at A, and see what that power series has to look like. And what we saw last time was that the coefficients have to have a certain form. And here it is in all of its glory. Right? The nth derivative of our function evaluated at our center divided by n factorial. That's the coefficient that gets multiplied on our just x minus our center to the n piece over there. All right, so this is what it looked like in summation notation in standard form. Written out in expanded form, it looks more like this. We talked about how really the only thing that we need to do to figure out this Taylor series, and we said that either one of these is called the Taylor series. Let me just write TS here, Taylor series. In order to find what this Taylor series is, we really just need to figure out what all of these derivative values of our function evaluated at our center are, and just plop them in where they go. So we can do that one at a time in expanded form here, or if we want the summation notation standard form, we need to figure out the formula for the nth derivative evaluated at our center. And last time we went through this process for e to the x as our function. We just started cranking out derivatives and saw that, well, the derivatives aren't going to change very much. The nth derivative is just e to the x. And then plugging in our center to these, we get 1, 1, 1, and so the nth derivative evaluated at 0 is going to be 1. All right, and so this 1 here, we can just take and plop in where we see the nth derivative of our function evaluated at 0. And what we get then is our Taylor series for e to the x is 1 over n factorial times x to the nth. And just sliding the x to the n up top, x to the n over n factorial, that's a nice clean way to think of the power series for e to the x. And if we write that out in expanded form, first term's 1, then x squared over 2 factorial, x cubed over 3 factorial, nice and clean power series for e to the x. And so today, we're going to have a chance to work through this process and find Taylor series for sine and cosine. And so if you haven't had a chance yet to start working on the power series, Taylor series for sine of x, now is your chance to do that. Just a quick reminder here. So the first problem up here says compute the Maclaurin series for sine of x. Maclaurin series, all that means is we're looking at a Taylor series with center 0. That's what a Maclaurin series means. See if I can do this. Almost there. 0. That's what it means. Maclaurin series is just a Taylor series centered at 0. And so over here, you can already see I've started filling this in. If you haven't worked through this for sine of x already, pause the video right now, compute a bunch of derivatives, and plug in our center, and then follow the instructions here on the left and see if you can get a nice standard form for the Taylor series for sine of x. All right, now that we had a chance to work on that, let's talk about it. So here's what I got for all my derivatives, just cranking through those. For each of those, we can plug in our center, 0, 1, 0, negative 1, 0, 1, 0, negative 1. See a pattern going on. And so each of these values, we can now plop into where they go in our kind of Taylor series form here. Right, so this is just, let me scroll up, this is what we have here, just with keeping in mind that our center is 0. So f of 0, f prime of 0, and x minus 0, we can just write as x, and so on. And so here we know that we have this basic structure here. And so we can just feed in for f of 0, f prime of 0, f double prime of 0, f triple prime of 0, fourth derivative at 0, just from our list here. It's going to be 0, 1, 0, minus 1, etc. Just plop them all in. So when we do that, our first term, f of 0 is 0. Then we get 1 times x. Our third term, 0. And minus 1 over 3 factorial times x cubed, and 0. And so on. Right, of course, we don't have to write all these plus zeros. If we get rid of those, oops, oh, there it is. Then this is what our series boils down to. And so here we can kind of see a pattern here going on. This is a perfectly good expanded form here. We want to write that into standard form. We need to come up with kind of a formula for the nth term here. And so here we can notice some patterns. Our terms are alternating, positive, negative, positive. Our powers on x are all these odds going up by 2 each time. And the factorial in the bottom just matches the power up top. And so here is one way, if we start indexing at n equals 0, that we could capture that. We have our alternation term here. So we need the nth power so that when we plug in 0, we get positive 1, since our first term is positive here. And then we want to start at first power of x, go up by 2 each time. So the 2n plus 1 will move us through 1, 3, 5, 7, and so on. And we just need our factorial at the bottom to match the exponent up top. And so here we could just see right away that we're going to need 2n plus 1 factorial. Right? And so this is our nice power series representation for sine of x. And we can see this converging to sine of x real nicely on Desmos if we jump over there. Looks like I have up already the power series for e to the x we looked at last time. Let me switch over. Stand by. 1110, where is it? I just had it, there it is. So there's our e to the x one again. Let me close that. So sine of x, here is the general term that we found. Now if I slide up our index here for the top, we're going to be including more and more terms. And so here we see just y equals x, our very first partial sum. And if we slide that up, we'll include in more and more of those. So here's now the cubic, then the 5th degree, 7th degree, 9th degree. And once again, we can see our red curve doing a better and better job of hugging the sine of x curve as we include more and more terms. And we can also see, right, there is this kind of freaking out on the side that's happening, but right, that freaking out isn't hitting a wall, it's spreading out. And in fact, the power series for sine of x does equal sine of x for every x. There's no finite radius of convergence. It converges everywhere. All right, switching back to our PDF over here. So there's the story for sine of x. If you haven't had a chance yet to work through the same procedure, cranking through derivatives, evaluating at the center, and feeding in, seeing what we get, for cosine of x, pause the video here and take a minute and work through that and see what you get. All right, so let's talk through that. I have it on a separate page down here. So what we're doing here, kind of cranking through the derivatives, this is what we call using the definition of Taylor series to work through these. And so here are all my derivatives for cosine of x. Just cranking through those, plugging in our center, a equals 0, 1, 0, minus 1, 0, 1, 0, minus 1, 0. And so now feeding those in where they go, right? The 1 becomes our first term, and then we get, because of the 0 here, we'll have 0 on our second term. This minus 1 goes in the numerator, minus 1 over 2 factorial x squared. All right, the 0 is going to make our next term 0. And then similarly, right, the 1 plops up top here, 1 over 4 factorial x to the 4th, then 0 minus 1 over 6 x to the 6th, just x to the 6th, and so on. Right, so once again, we can kind of collapse this down. We have a whole bunch of zeros. So if we get rid of those, we get this nice power series. And now, actually, we see that all the powers we have of x are even, as opposed to sine, which has the odd power. And so right here, this is a, again, nice expanded form for cosine of x. And if we want to write this in standard form with summation notation, we just need to come up with our kind of pattern here. And again, we have alternation, positive, negative, positive, negative. We have even powers of x and the same exponent down in the bottom. And so it'll look pretty similar to sines. We have our alternation here, the nth power is giving us a positive when we plug in n equals 0. To get our even powers, we can do x to the 2n, and then just grab that, and we want that factorial in the denominator. And so this is a nice standard form way to remember our cosine Taylor series. And once again, we can see that on Desmos if we jump over there. So there's cosine, and here's the series that we just found. And so it looks like starting out, yeah, we have just our constant y equals 1. And if we bump this up, we'll have our degree 2, then our degree 4, degree 6, degree 8, and again, doing a better and better job hugging cosine further and further out. And this power series for cosine does indeed converge for all x. Whee! All right, so last piece today is getting this cosine power series, but in a different way. So, right, we have this connection between sine and cosine, that the derivative of sine is cosine. Well, we can make use of that. We have a power series for sine of x, right, from the first one we worked today. Well, we can now take the derivative of that power series to get one for cosine. And so if you haven't had a chance to work through that yet, pause the video here, take a couple minutes, and see if you can work through what that looks like. And we'll start when you're done. All right, so let's see what that looks like here. And here I'm just copy pasting our formula for the Maclaurin series for sine of x that we found earlier. And we're just going to differentiate both sides here. And so differentiating sine of x gives us cosine of x, and differentiating this power series, right, in standard form, we can do that. We just got to remember that, right, for each index n, this minus 1 to the n over 2n plus 1 factorial, this is all going to be actually just some big ugly constant multiple. Constant multiple. And so we can just ignore it in terms of taking the derivative. It's just going to hang out. We really just need to take the derivative of the x to the 2n plus 1 factor up there. And so taking the derivative, just using the power rule, 2n plus 1 comes down. There we are. And our exponent drops by 1 from 2n plus 1 down to 2n. And so this is what we get after taking the derivative. But we can do a little bit of simplifying here, right? We have 2n plus 1 up top and 2n minus 1 down here at the bottom. And so we can make use of how factorials are built and pull off that first top factor, if you will. And then what's going to be left is just dropping 1 down from 2n plus 1 to 2n. It's that factorial, right? And so separating off that top factor, that'll cancel off with the 2n plus 1 up top. And we're just left with the 2n factorial in the bottom. And once again, we get this Taylor series for cosine of x, and it does exactly match the one that we found just a few moments ago. So that's another way that we could get at that. All right, good work today, and I'll see you in the next video.